class is going to be mostly about discussion of some problems, and particularly if you have any doubts in HC Verma in your module, we'll discuss about that also. So you can start by sending me any doubts that you have from HC Verma. Let's cover that first. And while you are sending me the doubts, I will put up a couple of questions. So in the meantime, you can keep doing those questions and we'll discuss those also. So I'm starting with some, you can say, sort of revision problems or exercise problems, which you can do for practice for work by energy. And going along, I'll be discussing any particular doubts that you have from HC Verma and later the module also. So let's do some revision questions. So we'll start with this example. We have a one-dimensional motion for a particle of mass 2 kilograms, okay, moving under the action of conservative force only, along the x-axis, such that its potential energy is given by the formula x square minus 30x plus 200, where x is in meters and potential energy is in joules. Okay, so if the particle has a kinetic energy of let us say 30 joules at the point x equal to plus 12 meters, okay, then find the maximum kinetic energy during its motion maximum range of displacement during its motion. That is the change in x coordinate delta x. What is the maximum value of that parameter we have to find? And the plot the kinetic energy versus x and also the potential energy versus x graphs for its motion. So start with this question and we'll discuss few more questions as well as doubts in today's session. Okay, I've got your message, Aman. Thanks for it. I will start with some of these questions from HCV. Actually, both the Amans, Aman Ranjan and Aman Agarwal, I have received both your messages with doubts. So I'll be discussing these questions in few minutes. Yeah, Ayush, so we will see that similar concept in this question also, whether the graph is given or the formula is given for potential energy. The equilibrium points are the points where the rate of change of potential energy is zero. Na? So du by dx is zero. Now, that is nothing but in terms of graph, it is a turning point of the graph. So it's the point where we have either local maxima or local minima. And stable equilibrium is at which point where there is the local minima, whereas unstable equilibrium is at which kind of point where there's a local maxima. Whereas there's also a third type of equilibrium which is called neutral equilibrium. That happens if the potential energy is a flat line graph, like a horizontal straight line. So the potential energy is just constant. So force is zero at every point. So there is neither restorative force nor non-restorative force because the force is uniformly zero everywhere. So that kind of situation is called neutral equilibrium. Whereas for stable equilibrium, you need restorative force at the neighboring points. So it should be a local minimum. And for unstable, you need the non-restorative force. So it should be the local maxima. So we will in fact be using that concept in this question also. Solve. Okay, so please send me the answers in case anybody has solved this, the first part at least. Yeah, Kevin, let's look at the answer. I think your answer is correct. Okay. So our potential energy function is like this. U is equal to, how much is it? X square minus 30x minus 200 is that the value, sorry, plus 200. So we can see this is rather easy type of function to factorize. It is x minus 10 into x minus 20. Okay, so it's easy to visualize that your potential energy graph is having the roots at 10 and 20, and therefore it is having a local minimum at 15. You plot your potential energy versus x. It's easy to understand this, that at 10 and 20 you have the roots. So the shape of the graph will be something like this. So parabola like this. Okay, so the minimum potential energy will be at 15, and minimum potential energy will be equal to, you can see 15 minus 10, that is 5, into 15 minus 20, which is minus 5, so that will be minus 25 joules at x equal to 15 meters. Okay. U is equal to 0 at x equal to 10, 20. So these are the roots of the quadratic equation. So this is the minima point, minima or vertex at x equal to midpoint of the roots. So that is 15 meters. Okay, now what is happening is that our 12 point is something like this. Okay, so at x equal to 12, we can see our potential energy would be 12 minus 10 into 12 minus 20, or 2 into minus 8. So minus 16 joules. And our kinetic energy is given to us as, how much was it, 20 joules or 30 joules, right? So kinetic energy is 30 joules, that was given. Okay. So we can see that from the data about this, we know that the total mechanical energy is equal to 30 minus 16, or plus 14 joules. That is the total mechanical energy. Now, next thing that is given to us in the question is that non-conservative force is absent, external force is absent, because it says that only conservative force acts. Therefore, mechanical energy is conserved. Okay. So the sum of kinetic energy plus potential energy is equal to 14 joules everywhere. Everywhere it's equal to this. Okay. So now we get the idea from this that kinetic energy's minimum value will be 0, and potential energy's maximum value will be plus 14 joules. Kinetic energy's maximum value we can find out because potential energy's minimum value is equal to what? From here you can see it is minus 25 joules at x equal to 15 meters. So you can see that maximum kinetic energy plus minimum potential energy is equal to the total energy. So this thing, so maximum kinetic energy is equal to 39 joules. This is the maximum kinetic energy, and this will be when it is at x equal to 15 meters. So that's the first part done. This is the first part's answer. No, equilibrium is at the minima beta. So equilibrium is at 15. So this minima point, this is the stable equilibrium position. stable equilibrium. So if we place the particle at x equal to 15, the force on the particle, which is minus du by dx, will be 0. Okay, but you can also see from the graph that at x less than 15, the force will be negative of du by dx. So it will be a positive force. So it is restorative. Okay, whereas you can see in the graph, the slope is negative, so the force is positive. Whereas at x greater than 15, you can see the slope is positive, so the force will become negative. So again, it is restorative. So that is why this will be a system that is capable of oscillating, because there is a stable equilibrium point. No, but 10 and 20 are not equilibrium points, because there is some slope at those points. At 10, there is a positive force, and at 20, no. So unstable equilibrium doesn't mean that. Equilibrium का मतलब ही होता है जहाँ पे force 0 होता है. So there is no unstable equilibrium point because there is no local maxima. So this system, you can see, does not have any unstable equilibrium point. Okay. So this system only has one equilibrium point, which is x equal to 15, and that is a stable equilibrium point. Okay. That is again something that you can analyze from the graph. From the potential energy graph, you can see that the potential energy graph is a parabola like this. So it has only one equilibrium point, which is 15. From this graph, you can see that the system has only a single stable equilibrium point. At x equal to 15. All other points are non-equilibrium points. Okay, so that means there are points at which force is not equal to 0. The net force is not equal to 0. Okay, they are non-equilibrium points. Okay, so the rest is just calculation. You'll see it's quite easy. Yeah, good. Okay. So now we have to find the maximum displacement. So also see what is given to us about the mass of the particle, it's 2 kg. So, the fact that its kinetic energy is 39 joules and the mass is 2 kg, it will also tell you that its velocity will be plus minus root 39 because the mass is 2 kg. Every time it is at x equal to 15 centimeters. Sorry, meters, which is a stable equilibrium point. Every time it is at that point, it will be either going towards the positive side or going towards the negative side with a speed of 39 square root of 39 meters per second, which is very close to 6 meters per second. Okay. Now let's understand the other thing, the range of the motion. So let's come to that. That's very important. So we can also see that the let's start by the u versus x. Now we can see that total energy was, how much was it? 14 joules. So at points where kinetic energy is zero, that is the minimum possible kinetic energy. Kinetic energy cannot be a negative quantity. Potential energy is maximum. Okay, so these points are where this thing should be zero, then this thing is maximum, and this is 14 joules. Okay, so maximum potential energy, which is your x square minus 30x plus 200 is equal to 14. So when we solve this, we'll get some two values, x1 and x2. So these will be the range of motion. Okay, so it might take a little more effort to solve this, but this is how we will get the range of motion. So I'm just explaining. So now we have to solve this as a quadratic equation. Then we'll come back to the graph of potential energy versus x. So x square minus 30x plus, this time you will get 186, right, minus 14 is equal to 0. So we can just use this minus b plus minus b square minus 4ac divided by 2a. So you can see that these will be 30, or if you take this as 15 plus minus. So let's work this out now. So this will be square root of, you can actually take 4 common outside. So it becomes square root of 15 squares are 225 minus 186. Okay, so this is where do a bit of calculation. Square root 39. Which is approximately 15 plus minus 6.25. So one of these points, let's take as x1, will be approximately 8.75 meters, and the other point x2 21.25. So this is the range of motion. Okay, so these are the extreme positions between which the particle will keep loitering around, so to speak, because the potential energy will have a maximum value, which we saw was how much? 14 joules. So this is at maximum value 14 joules, and correspondingly the minimum value was minus 25 joules. Just 1 minute, guys. I'll be back with that. Yeah, so the minimum value of potential energy was minus 25 joules, and this is happening between x1 and x2, which are symmetric with respect to 15. So you'll see that the potential energy graph, let's say, going to be something like this. This is occurring at 15. this is occurring at that point x1, which is this value 8.75, and this is occurring at the point x2, which is 21 point, sorry, my mistake, not these points, these are 10 and 20, but rather the extreme positions of the motion. So that is this point here, where the potential energy is becoming maximum. So this is your 8.75, and again this point here, which is 21.25 x2. So this is the overall range of motion. So you can understand that the particle does not have enough energy to go beyond 21.25 or come before this. It keeps loitering between these 2 points. So this is, in fact, we can take in red color, we have taken the potential energy graph. So U is equal to that function x square minus 30x plus 200. But for that range, in this particular case, it's only going between x1 and x2. Because at those 2 points, we'll see next that the kinetic energy becomes 0. Okay, so you can see that since kinetic energy plus potential energy is constant, so the kinetic energy as a function will become this. So 14 minus of x square minus 30x plus 200. So the kinetic energy is in fact 30x minus x square minus 189. This is the kinetic energy as a function of x. So if you look at this kinetic energy function within the same graph, that will be a function which has a maximum value of 39 and a minimum value of 0 between. The kinetic energy ranges between 39 joules and 0 at these 2 points. नहीं बेटा, kinetic energy cannot be a negative quantity. Na? Kinetic energy cannot be a negative quantity. It's half mv square. Na? So its minimum value is okay. That constant here, yeah, correct. It should be 189, 186. That's correct. Okay. So the range of kinetic energy is between 0 and the maxima, which is 39 joules. Okay. So you can see that delta x is maximum is x2 minus x1, which will be approximately 12.5 meters. So it will actually be like an oscillation where x equal to 15 is the mean position of the oscillation. So speed is maximum, potential energy is minimum. Whereas on either side there is an amplitude of 6.25. So these become the extreme positions of the oscillation. Keep backing and forthing between the extreme positions where V becomes 0 and potential energy is equal to plus 14 joules, which is the maximum. So this is the complete analysis. Okay, now let's pick up some of those questions from H.C. Verma. The difference between the two parabolas, Ayush, is that, you know, one parabola is negative coefficient of x square. So if you have, and this, if E is a negative quantity, then it's always a parabola that looks like this. Okay. Doesn't matter where the xy axis is. It could be like this, in which case it has two real roots. Okay. It could be like this, in which case it has one common root. Okay. It could be like this, in which case it does not have any roots. It could be like this, in which case one root is negative, one root is positive. All this is possible. Okay. Whereas another situation could be where the coefficient of x square, yeah, I'll come to that. If E is positive, the coefficient of x square is positive, then in general the parabola will open upwards. Okay. So again, it could be a parabola with, you know, different situations with respect to the axis. So it could have two real roots. Okay. It could have a single root. It could have imaginary roots or no roots. It could have one root negative, one root positive. Okay. But either way, it will be a parabola opening upwards if E is positive, if it is opening downwards if A is negative. So this is the difference between the two types of parabolas. Now, so coming back there, you can see the potential energy function is having positive coefficient of x square. So it's a parabola opening upwards. Whereas when we have worked out the kinetic energy function from that, you can see it's a parabola which is opening downwards because the coefficient of x square is -1 for the kinetic energy. So look at the difference between this relationship, which is the red colored parabola, and this relationship here, which is the blue colored parabola. At the same time, they have a nice symmetry to them because simultaneously at the point where kinetic energy reaches its maximum, potential energy is reaching its minimum. So they are having the common x coordinate of the vertex, which is nothing but the equilibrium position of the system. But mind you, they are not having common roots because kinetic energy is becoming 0 at 8.75 and 21.25, whereas potential energy is becoming 0 at 10 and 20. The roots of the potential energy function is in this point is 10 and this point is 20. So they're different in that sense. Okay, so I hope this clears all the points. U minimum जो calculate किया था Nikita, I'll just take you to that once more. So that is basically coming from this one, parabolas. So you can also use maximum minimum to calculate U minimum. You have got this function x square minus 30x plus 200. So to calculate the minimum, you can also do this. You can also use differentiation method. You want to calculate the minima. So du by dx should be 0 and second derivative should be positive at the point where we have max a minimum. It's a local minimum. But I have avoided that because it's a quadratic function, and quadratic functions graphs we know inside out, because parabolic graphs are so common in physics, right from your uniformly accelerated motion, projectile motion, vertical motion. All these have parabolic graphs. In vertical motion, the displacement versus time is a parabolic graph. So we should be well practiced in this. Okay, it's very important in physics. Okay, Amog, I'll show you the question once more. Okay, uh, let's come to some of the questions from HC Verma. So Aman Ranjan, question number 21 and 23 and 26. Okay, let's quickly discuss these. So a couple of these questions are pretty straightforward. So I'll just quickly tell you what to do. So coming to the doubts from HC Verma. In question 21, it's a pretty straightforward thing actually. A projectile is fired from the top of a cliff which is 40 meters high with a speed of 50 meters per second but unknown angle. So this is where you can see that if you use work energy, you'll get the answer very fast. You're just projecting it at some speed you don't know this angle. You know this speed is whatever 50 meters per second. Okay. Now just use work energy. No? During the projectile motion, there's only gravity doing work, and gravity is a conservative force. So if this has a final velocity v with which it's hitting the ground, half mv square minus half mu square, this change in kinetic energy, minus mgh, the change in potential energy, should be 0. In this, just substitute h as 40 meters, substitute u, get v as square root of u square plus 2gh. That's why the mass is not given. Okay, so you can do it this way. No need to apply the projectile motion equations because you're only finding out the speed. Okay, now let's move on to 23rd question. So it's talking about an athlete who won the 100 meters sprint like this. Okay, record time of 10.54 seconds. So assume that she achieved her maximum speed in a very short time, and then ran the race with the speed till she crossed the line. So the kinetic energy at her full speed that you can find out is very easy. So assuming that the time taken to achieve that speed was very less. So if we assume that over here, so we can visualize a velocity time graph. The athlete's velocity time graph for question 23. We can assume that is something like this. Accelerates very, very fast. So assume something like this. And then maintains almost the maximum speed throughout the race. So this total time is given to us as 10.54 seconds. Okay. Whereas this time for which she is accelerating, this delta t, okay, now if delta t is negligible, that means delta t is very, very small compared to 10.54 seconds. So then we can take the area of this graph, which is the displacement, as more or less equal to Vmax into 10.54 seconds. And this is given to us as 100 meters. So it's more or less equal to, so we can find that Vmax from this. Something slightly less than 10 meters per second. And then from that you can find the kinetic energy. Yes. And then while that person is running, they're running at speed like this. Now there is some kind of resistance force, which is approximately, they are saying, equal to 1/10 the weight of that person. Okay. And then they make that displacement of 100 meters. So you have to just calculate the work done by this resistance force. It will be minus of that resistance force into the displacement, because it's in opposite direction. So the mass of the athlete is given that the resistance force is 1/10 of the weight. So it's acting against the direction of motion. So that's how you can calculate this. Okay. Now what power she had to deliver to maintain this speed? So is going at constant velocity. So acceleration is 0. So she's generating a forward force by pushing her leg back against ground. So that forward force is balancing the resistance force. Understanding, Aman? Because the acceleration is 0. So the forward force that she is generating from the ground is also equal to mg by 10. So the power delivered by the force she is generating by pushing the ground back, that is equal to F into V. And this V is more or less the V max, because she's running at V max. Okay. So that is 1/10 of her weight into this velocity, which is approximately 100 upon 10.54 meters per second. So that will give you the method for calculating the power. So hope this is clear, Aman. Okay, let's move on to the next question. Okay, 26th question. You are lifting a mass of 2000 kgs through a distance of 12 meters in 1 minute. So horsepower of the engine you require to find out. So you have the mass, which is 2000 kg. You're lifting it through a height of 12 meters in a time interval of 1 minute or 60 seconds. Okay. So your work done is equal to the change in gravitational potential energy. So that is mgs upwards. Okay. So your average power delivered by the engine will be work done upon time. So it will be 2000 into 10 into 12. This is in joules divided by the time, which is in seconds so much. So this will be your power in watts. Whatever you get here, it will be your power in watts. And then use the relation that 1 horsepower is approximately 746 joules. Sorry, watts. Okay. So to convert that into horsepowers. Okay, next I'm coming to question number 49. And you don't have to memorize this horsepower thing, because it's not really part of your syllabus. Snikita, sorry, I just saw your message. It is going to be a simple harmonic motion, that one, because now why it's going to be simple harmonic you will learn later, because in the chapter of simple harmonic motion you learn the relation that the restorative force has to be proportional to displacement from the mean position for SHM. So whenever your potential energy is a quadratic function with a stable equilibrium point, so its differentiation is a linear function. So that means the force is a linear function of displacement. That means the force is directly proportional to displacement from mean position. So yes, whenever you have this sort of a parabola for potential energy, which is quadratic with respect to x, you do have an SHM. Okay, but that is not important for us just now in this chapter, because we haven't learned the proper dynamic condition for SHM yet. So need not worry about that just now. Is it clear, Nikita? Yeah. Okay. Yeah. So let's move on to just a second. There is, I think, question 32. Is it also which we have to do? Yeah. Okay. So 32 is also a bit of a conceptual question. So unlike the applications of vertical circular motion that you have done in that chapter, where you have a frictionless kind of situation, or no air resistance, here you have to assume that inside that tube there is some friction actually. Okay, so the object that is doing that vertical circular motion eventually comes to rest. So imagine you have some kind of a tube like this. Now there's a particle that fits into the interior of the tube, but there is also some friction. Okay. So this is in a vertical plane, but there is some resistance force, or there's some friction. So what happens in this question is that mass of the particle is given, and at the highest point we push it off with a speed of 5 meters per second. So it will keep going back and forth, and like this, but it will keep losing energy, assuming that there is friction and non-conservative force like that which is dissipating energy. So it might go like this, but then return back, and after making several such back and forth journeys, it might eventually come to rest at the stable equilibrium position, which is below. So we have to find the total work done in this case by non-conservative forces, no, because it will be dissipating the energy. So you just use this theorem, no? Work done by non-conservative by work done by external is change in kinetic energy plus change in potential energy. So here you take the particle plus gravity as your system. Okay. So your change in kinetic energy will become minus half mu square, and your change in potential energy will become minus mg into 2r. Okay, and this is zero because normal reaction is not doing work. So this is work done by friction or whatever. So that's all you have to do. So hope this is also clear. So when they are saying find the work done by the tube on the block, so it's obviously the frictional force inside the tube which is doing the work. The normal reaction is not doing any work. It's the frictional force inside the tube which is doing the work. Okay, right. So now let's move on to question 49. Now that's a very interesting question, and we have to develop a nice constraint relation for it also. So I will start by giving you some hint for question 49, and then we will discuss it in detail. So if you haven't worked it out, just try to at least get the equations right now. So we have this kind of a system. Oh, sorry, this is question 50. Yes, you're correct. Yeah, correct. This is question 50. That is the one I intend to discuss. So A and B both have the same mass, and it's not as simple as this. There's also a spring. So initially we release the system from rest where the spring is actually natural length. Okay. So we release it from this state. Now what we have to do is we have to find the speed of the block when A is about to lose contact with the ground. So we release it from this position, and we have to find. Okay, so some all data is given. The mass of the blocks is given 320 grams each, okay, and the spring constant is given, and this length is given. So this length is 40 centimeters. The spring constant, so that's the natural length of the spring. Okay. Spring constant is given as 40 newtons per centimeter, and the mass of the blocks are given as 320 grams. You have to find the speed of B, speed of A, whatever, at the instant when A is going to lose contact with the smooth surface. This, mind you, is a smooth surface. Okay, so this is the data given to us. So let's understand how the system will actually progress. So from this initial state, the moment we release it, what will happen is, because of B's weight, B will tend to pull A towards the right, while itself it will displace downwards. So the moment that happens, A will pull on the spring, and the spring will tend to get elongated. And as it gets elongated, it will apply a spring force in the sort of diagonal direction. Just a moment, people. Yeah, so just a moment, people. Yeah, so here, after some time, something like this happens. This block has gone here. By the time this block has displaced to here, right? So this is the position of the system after some time, when the spring has got elongated like this. Okay, so let us say that A's displacement has become S and A's velocity has become V. Now, because they are connected by a thread like this, you can see B's velocity will also be V in magnitude, that is, okay, and its displacement will also be S. And the springs would have stretched now to L plus X, like this. Okay. So if you compare the two diagrams, you can get some kind of relationship between these two. So first of all, you can see that L plus X is equal to square root of L square plus S square. So X is equal to square root of L square plus S square minus L. Okay. Or if we take this angle here to be theta, you can also express everything in terms of theta. We can see that L plus X, okay, is equal to L upon sine theta. Correct. This thing is L. This thing is L plus X. I've taken this as theta. So like that. Okay. So I can do this also. Okay. And I can express S as L tan theta. This is also one convenient way in which we can express everything. Now let's look at the free body diagrams. So A is free body diagram. There is Kx acting such that this is the angle we have taken as theta. There is Mg acting, and in general there is normal reaction acting, but we will be also interested in the instant when normal reaction becomes zero. Tension like this, okay. And B is free body diagram, of course, only tension and weight. Okay. So two things we will do now. One is we will use the free body diagram of A to apply the condition for A to lose contact. Okay, and that condition is that the normal reaction should become zero. So you can see Kx sine theta, that is the vertical component of the spring force, should balance mg. So that is my equation one. And the other thing I will do, I'm just writing down here, we'll implement it later. If you take A plus B plus the spring plus gravity as a system, okay, then to that system you can apply conservation of mechanical energy. So these two things we will do. So we'll write an equation for that second thing, and we will solve the two equations using these sort of constraint relations in between. The relationship between x and theta and the relationship between s and theta. We'll have to make use of these two equations also. So let's write these as equation 3 and 4. These are like geometrical constraints. They are not really physics equations, but they are just giving us the geometrical relationships. Okay, so just try this out now. So the solving can be a little bit tricky, so that's why I'm asking you to just frame the equations properly. We'll discuss. Yes, in the fourth equation, we'll have to substitute like that. Sorry, S will be equal to L cot theta. Make a correction here. So anyway, let's come to the work energy relation. So we can see that half mv square plus half mv square. This is change in kinetic energy of A plus change in kinetic energy of B. Okay. Minus mgs, that is change in gravitational potential energy of B, plus half kx square is equal to 0. So we have mv square is equal to mgs minus half kx square. This relation. Okay. Now, so this is our second equation. It's coming from work energy. Now in this, from here, we will substitute x as L by sine theta minus L. Okay. And from this, we'll understand that this is equal to mg upon k sine theta. So we have a relation like this. This. Okay. So L is given to us, mg is given, k is given. So from this we can find theta. Okay. So once we have found theta for this equation, we know the value of x, know the value of s, and we can find out the value of b. So let's substitute this. Okay. So 40 centimeters, 40 newtons per centimeter, and 320 grams. Okay, so this relation becomes like this: 0.4 into 1 minus sine theta is equal to 0.32 into 10, 320 grams into g, 40 into 10 raised power 2. So from this we'll get sine theta. Just take my calculation. Simply getting something done like me. Oh, sorry, it was 40 newtons per meter. The spring constant is not 40 newtons per centimeter, rather it is 40 newtons per meter. That's what I thought. This is not in newtons per meter. So when we substitute this here, this factor will not be there. So this will become 10 raised power minus 1. think we'll be getting sine theta as half, right? Oh, sorry, 1 by 5. Sine theta will come out 1 by 5. So our x will come out what now? So 4L. Okay. So we'll substitute x over here. Okay. And we'll get s as L cot theta. Sine theta is coming 0.8. You sure? How? Okay, I made some mistake again. That means oh, sorry. Yeah, 1 minus sine theta is 1 by 5. Correct. Yes, that's correct. This is not sine theta. This is 1 minus sine theta. So this is 1 by 5. Okay. So sine theta will become 4 by 5. So that makes life even easier. It is a known angle. So theta is 53 degrees. So anyhow, so that now makes this so 5 by 4 minus 1, so L by 4 or x will become 10 centimeters or 0.1 meters, and s will become L cot theta. So that become 40 centimeters into cot of 53, so that is 3 by 4. So L will become 0.3 meters. Sorry, S will become 0.3 meters. Right, so now in this equation we have to just substitute mass as 0.32 kg, substitute spring constant as 40 newtons per meter, g as 10 meters per second square, s as 0.3 centimeters, and x as 0.1 meter, and calculate the value of v. So that's finally how we solve this question. Okay, so hope this was clear finally. A bit of struggle. Okay, next up we have to discuss question number 63 and 64. If anyone has a doubt in a question before that, please let me know. We'll discuss. Oh yes, question 58 number. Yeah, I'll come to that. So let's discuss question 58 next. Okay, next up, let's come to question 58. So we have basically like a pendulum kind of situation, but also a case of vertical circular motion being incorporated. It says that there is something like a like a nail or a peg coming out of the wall at the point X like this. So if you see the side view of this wall, so it's a vertical wall like this, and the pendulum is suspended from this point O. So let's say the point O is somewhere here, from where the pendulum is suspended. So there is a peg like this which is jutting out on the wall at a distance X below this. So when a thread hits that, it will tend to go around that peg. So that is the concept in this question. Okay. So assuming initially the bob has a height less than the peg, show that the maximum height reached by it equals to its initial height, A part. So A part, we are assuming that, as you can see in this diagram, this is at a higher height compared to this one. The peg is at a higher height compared to the bob's initial position. The bob is lower, the peg is higher. So you release this from rest over here. So then what happens is, it's quite easy to understand that by the time after releasing it, by the time this becomes straight here like this will have some kind of velocity, let's say V naught. Okay. And after that, what will happen is that it's going round the peg. So it will not be doing circular motion about O, but instead it will now be doing circular motion about the point P. So it will go into this kind of circular path. Where the radius of the circular path will become L minus X. But from simple work energy, we can see that at the maximum displacement position, again the velocity becomes 0. The potential energy should be the same now. So that's why it should come to the same height. So that is your A part actually. You have to prove that this height is the same. So this part of the circular motion is happening about this center, it's coming like this. Like this. But next it is going into a circular motion about this point. This radius R, like this. Okay, so you can see that here minus mgh plus half mv naught square is equal to 0. Okay, so it has to go to the same height. So if you assume this height is some h prime, you can understand that this is equal to mgh. So h prime has to be equal to h. So that is the first part. Okay. Now the second part, what is happening is that if it is released from 90-degree position and x is equal to L by 2, we have to find the maximum height reached by the bob above its lowest position. So next we are releasing it from theta equal to 90 degrees, u equal to 0. Okay. and x is at L by 2. So we have to find the maximum height. Okay, so let's understand this next. So in this case now we are releasing the bob from the position where the string is just about horizontal. So we are releasing it from this position. Now the peg P is at x equal to L by 2 below. Okay. So first part of the journey is the circular motion about the point O, about the point of suspension above. So when the string is about to hit the peg, your situation will be almost vertical like this. Okay. So it has some speed V0 at the bottom. So it has covered this kind of circular path about the point O. Okay. So your first step is the work energy relation. So half m V0 square minus mg L, because the vertical displacement here is L, is equal to 0. So your V0 is root 2g. Okay. But also now what is happening after this? This is going into a circular path about the point P. So from here on, it's going into a circular path of radius L by 2, going to this kind of circular path. So also you can see that this in terms of that radius is root 4 gr. So you can see that V0 is less than root 5 gr, but at the same time greater than root 2 gr. So this is that situation where the thread will slacken at some position. So from here on, it will go to some position like this, where the thread will suddenly slacken. So the tension in the thread will become 0. And let's say it will have some speed V1 at this position. Okay. And then from there, what will happen further? It will go into projectile motion. So it will go into projectile motion and fall like this. So somewhere here, it will reach the highest point. So that P is the highest point with respect to, let's say, Q, where Q is this point. So our objective now is to find that highest point. Now, a lot of times the students, when you're doing this question, you might make a mistake that you finding the point where this thread is slackening. This point's height you're finding with respect to Q, and you're giving that as the answer. But you forget that even after that point, it's in projectile motion. So it does climb a little bit higher. Then only it comes down. Understanding? So let's say we call this point something like S. So at S, what is happening? The thread slackens. That is, tension becomes 0. So from S onwards, it's not coming down vertically now, because the particle is not at rest at that point. So vertical circular motion, to understand. So from that point onwards, it is a projectile motion. So let's see how we can use work energy theorem very effectively. And in that projectile motion from S to P, it's still climbing in height. Okay. That is why P is the highest point. Okay. So now the key thing is this calculation here, that our velocity at the bottommost point is root 4 gr, and of course r is L by 2. So let's come back to concentrating on this part of the motion. Just to help me out, I will draw a circle like this. Then So now coming back to our situation here. Let's say this is where the peg P was, whereas this is the point O. So this is our R equal to L by 2. And at this point we had a velocity which was root 4 GR or root 2 GL. Okay. Now comparing with that, we are looking first at the point where it's losing tension. So let's say that point is here somewhere. So this was our point Q, and from that it's coming to this point S, where the string slackens, the tension in the string becomes 0. So at this point of time, let's say it has a velocity vector. So tangential velocity, because just now only the string is losing tension. So up till this point, it's still circular motion. So this velocity here is some v1, let's say, okay, and this angle becomes some theta. So you can see that this angle is also theta, because after all the velocity is along the tangent. So this angle is 90. Okay, so the fact that tension is becoming 0. So if we look at the free body diagram, mg, okay, it has a speed v1, and this is your radial direction, this is your tangential unit vector. So here this angle will be theta, because mg is acting vertically downwards. So this angle is theta. So the condition for normal reaction to become 0 is that mg is the centripetal force. So it's mv1 square by r. Sorry, mg cos theta is the centripetal force. The centripetal component of mg is only this. So that's our first equation. That's one condition we understand for losing tension at that, sorry, not normal reaction, for losing tension at this point. The condition for tension to become 0 is this. So v1 square is gr cos theta. That's it. Okay. And the other is we can apply work energy or conservation of mechanical energy from Q to S first. We do that. Okay. So this is my small h, let's say. So you can see that small h is r into 1 plus cos theta. Okay. So half m v1 square plus mgh is equal to half m v naught square. So this is my second equation, which is the work energy relation or conservation of energy relation. Now solving of 1 and 2 will give us theta. That's the first thing we need to do. Okay. So v1 square is equal to v naught square minus 2gh, and substitute this here. So that is v naught square minus 2gr into 1 plus cos theta. So now compare these two equations. Okay. Compare this equation, which is coming from equation 1 only, and this equation which is coming from 2. So from these modified equations, gr cos theta is equal to v naught square minus 2gr 1 plus cos theta. So we can see that 3gr cos theta is equal to v naught square minus 2gr. Right, and then we know this value of v naught. So substitute this here. So next step, 3 gr cos theta is becoming v naught square, which itself is 4 gr. Okay, minus 2 gr. So we're getting cos theta as 2 by 3, or theta as cos inverse of 2 by 3. But actually cos theta will be the more useful thing for us. So from that we are also getting v1, because that will also be useful. v1 is coming out to be square root of, from the first equation, gr cos theta. So square root of 2 by 3 gr. Okay. So just first make sure you're familiar with what we've done here. Now the last step is going to be very easy. We won't have to use projectile motion equations and all that. We'll just use a clever property of projectile motion, and we'll get the maximum height in one shot. Then I'll explain how that happens. Just note this down up to here till then. Yes, very good, Snikita. We will make use of that. And actually from the diagram now, you can see the horizontal component of velocity is how much? It is v1 cos theta only. Okay, so that's where application of work energy will become very easy, directly from the lowest point to highest point. You just use one equation for application of work energy from the highest point to the lowest, lowest point to the highest point. Okay, so first of all, hope this is all clear to you. Okay, now see what is happening beyond this. Now, we will get into the projectile motion part. Okay, to trace the highest point. So from here onwards, the motion of the particle is no longer along the circular path. It's along a projectile path like this. So when it reaches the highest point of its projectile motion, at that point of time, this is that point P. That particle's velocity, remember at the highest point of projectile motion, any velocity is only the horizontal component. The vertical component becomes zero. So at this point, so it's just Vx equal to, now from this diagram you can see that is equal to V1 cos theta only. Okay. So now ultimately see what we have to find out is this height. We have to find the height of the point P with respect to the lowest point below. So the height we have to find, now I'm labeling that height as something else, capital H, so that we don't confuse it with small h. So we want to calculate this height now. So we will go directly from Q to P, where because we know at the point P that we also have that additional information that the velocity is V1 cos theta. Okay. So now we can see at P, that is the highest point. Okay, V is equal to Vx, which is V1 cos theta. So that now we will copy paste from here. Okay, V1 itself was root 2 by 3 gr, and cos theta was 2 by 3. Okay, so now apply work energy theorem, conservation of energy from Q to P. Okay, so you'll have half mv0 square is equal to half mvx square plus mgh, where h is the unknown quantity for us now. So basically h is equal to v0 square minus vx square by 2g. Okay. So now v0 square was 4gr. Okay, and vx we just saw, vx is 2 by 3 root 2 by 3 gr. So इसका स्क्वायर कितना हो जाएगा? It will be 8 by 27 by 2g. So it is like r into 2 minus 4 by 27, something like this. Actually, in the question they have not asked this. The question they have asked small h only. Okay. So the question is slightly different actually. They have not asked capital H. They asked small h also. But I think there was an IIT, there was a question like this where capital H was asked. So anyway, if you have to calculate capital H here, it is L by 2 into, as you can see, 50 by 27. So that capital H will be 25 by 27 L, Whereas in this particular question in HC Verma, they've asked only the simple thing of small h, which you have already got actually here. So they've asked for the height of the point where the string becomes slack, for the point S where the string is slack for the first time. Okay, so that is just small h, which you can see is L1 plus cos theta. So that's pretty simple. So R1 plus, that you will substitute as L by 2. So that's how you will get 5 by 6L. Okay. But I think there was a similar question in IIT a few years back where the projectile motion's highest point was asked. So that if you have to calculate, then so you can add this to the question also actually. Okay, and then for the last part of the question, where you have to find that ratio of x by L so that when you release it from the horizontal position, it completes vertical circular motion. Okay, just give you the method for doing that. So there what you want is that when you release it from here, and then it comes and hits against something over here. So at the lowest point, it has a velocity of root 2 GL. So if this radius is becoming L minus X now, to complete the vertical circular motion, you know the condition is that this should be greater than equal to root 5 GR. You know that from your knowledge of this thing. So root 2 GL should be greater than equal to root 5 G of L minus X. So limiting condition will become that 2L is equal to 5 times L minus X, limiting condition. So from that you can find X by L ratio. Okay, so hope this question is clear. Now, two more questions I want to discuss, and since we are running out of time a little bit, so I'll take these up fast. So one is 63rd question. Now in 63rd question, what we will do is we'll use an integration kind of method. So we have this smooth spherical surface, okay, on which your chain was initially released from this position. Let's say this is the chain of mass m and length L, and its initial speed is 0. Okay. So we have to find the kinetic energy as a function of the angular displacement theta of the chain. This is a smooth surface. So it's starting from this position. Now after some time, okay, so after some time, let's say the chain has now come to this position, where it's slit down like this. So this length is L. But it's made an angular displacement of theta. So by now it's got a speed V. So we have to find that V. Okay. So what you do is, first of all, you take this angle as, let's say, alpha. So if the radius of the sphere is R, so you can see that alpha is equal to L by R. Okay. Now you take this as your reference level and integrate to find the potential energy U with respect to the point O. So in the initial diagram, U initial will become integration of So to find that potential energy, what we'll have to do now is that typical type of situation that at some arbitrary theta, you cut a slice. Okay. So the slice's length becomes r d theta. Okay. And with respect to this origin that has a y coordinate like this. Okay. So for that slice, you can see this is the potential energy. Okay. So where dm for that element will become mass per unit length into length of that. So m by L into r d theta, or m by alpha d theta, like this. Okay. And y coordinate of that you can see in the diagram is r cos theta. So this potential energy is becoming integration of m by alpha into r cos theta d theta. Now in the initial diagram, you can see it's from this point to this point. Okay. So this point is, let's say, A, this point is B. So integrating for all the particles from A to B. So your theta is going from 0 to theta equal to alpha. So you have this integration. Mr by alpha cos theta d theta. G is also there somewhere. Yeah. So this integration from theta equal to 0 to theta equal to alpha. So this will be your initial potential energy. Now the same thing you do in this diagram now. Okay, where you're taking, so let's take this angular displacement as some other variable, because I've already taken theta as that variable. So let's take the angular displacement as beta. Now, beta is the angular displacement. So we'll change that later. So this theta and all that, this r d theta and all that. So the same thing, the final potential energy is integration of dmg y. Okay, but now this point has become, let's say, c, and this point has become d. So c to d. So when you do this integration, again you have the same thing, mgr by alpha, but this at the point C, theta is becoming beta, as you can see. And at the point D, theta is becoming beta plus alpha. So you'll get some different value of final potential energy. And we've got some different value of initial potential energy. Now the difference of the potential energies is nothing but the kinetic energy. So you'll get half mv square plus u final minus u initial is equal to 0. So you'll get V as some kind of function of that angle beta. When you work it out, you will get V as some kind of function of beta. And then for the last part, what you can do is you can differentiate this. Okay. So you can take dV by, you can actually do like this only now, because your V, your instantaneous speed now is ds by dt, and that is nothing but r d theta by dt. Okay. So the acceleration, which is dv by dt, the tangential acceleration, is nothing but you can write it as v dv by ds. So that is nothing but v upon r dv by d theta. Okay. So in this, just replace beta as an instantaneous theta. Okay. And use this relation. So you get the tangential acceleration. So that will be about this question. So it's like, in 1D motion kinematics, you use that trick that okay, Ayush, I will go through that question and I'll send you some hints. Okay. So just like in 1D motion, you use the relation that A, which is dv by dt, can be written as v dv by dx if it's along x-axis. So like that in circular motion, okay, your tangential acceleration, which is rate of change of speed, can be written as v by r dv by d theta, because your ds is equal to r d theta. So this thing becomes, so you can always make use of this relation also, which I'm sure you've done as part of circular motion. Okay. So people, I'm running out of time. I have another lecture coming up. So 64th question, I will just give you a quick hint. So in that, what is happening is now the sphere itself is accelerating horizontally like this, okay, with a constant acceleration. So any particle which is sliding down the sphere like this, it is experiencing a pseudo force in the frame of the sphere. So if you are in the non-inertial frame of the sphere, there will be a constant pseudo force. F, which will be like this. Okay. So now you can do like this, that work done by the pseudo force plus work done by mg is equal to change in kinetic energy. But this is work kinetic energy theorem in the non-inertial frame of the sphere. Okay. So this work done will be such that, if the particle is going from here to here, let's say, so this is the displacement. So it has an x component like this and a y component like this. So you can see work done by the pseudo force will come out to be max, and the work done by gravity will come out to be mgy, and that should be equal to half mv square minus u square. But where this v and u are with respect to the non-inertial frame, they are not in the ground frame, they are with respect to the non-inertial frame. So apply that condition. Okay. Yeah, Ayush, I actually have to start a class, so I will send you the hint for that question later today. Okay, don't worry. Right. So Snikita, I'll show you the working of this question once more. Okay. I'll send you this thing the PDF anyway, so you can go through that. Okay. So I've not completed the question, but remember I've changed the angular displacement to the variable beta, because I've used theta as the variable for angular position, not angular displacement. So angular position of a particle. So in the final answer, you replace your beta with theta. Because in HC Verma, they've taken theta as the angular displacement. Okay. So we will more or less, we are winding up work by energy now. We will spend a bit more time in the next lecture discussing some more doubts and some questions from the module exercise also. But try to complete up everything, because we have a test coming up on 24th, I believe now. So that will have full work by energy applications, including vertical circular motion. Okay. So that's it for today, people. Wish you all the best.